Hello boys and girls, welcome to another episode of FoulkesBrau. So today we're going to do something very different. This is not something that we normally do on this channel. So this is really more aimed at the guys at school that are having to do a winter exam rewrite for maths for this year. But it might interest some of you, especially in the electronics world, because a lot of this stuff that we're going to do describes how things work. So today we're going to do a thing called ordinary differential equations, and we're going to use a technique called separation of variables to solve this. Now that is a hell of a big mouthful. What does it all mean? Calculus is a very good tool to describe mathematical models of how things work. So when they talk about a model, they talk about a relationship or something like that in how something works. So it could be a relationship between two parameters or something like that. So it might be a change in, let's say, the y-axis over the x-axis, or a change in some magnitude of something over time, velocity over time, for example. So that is what ordinary differential equations are. The problem is, as you can see in this form, you can't really do anything with that. So calculus, in other words differentiation integration, is very nice at describing the model. It's just not very user-friendly to actually do anything with it. So the point of ordinary differential equations of the first order, notice it's the first derivative, is to get this into an algebraic form. So we're going to start with our first question. We've got dy over dt equals 12 sine 4t plus t squared plus 1. Now you should be very competent at integration and differentiation now. So in Ireland you get this formula and tables book. You are allowed, they give you this in the exam. Everything we need to know, whether it is the rules of the integrals, the rules of the derivatives, and especially indices and logarithms, is in this book. So if you're not sure, refer to the book. If you get the equation in this form, you notice we've got no constant in front of dy dt. Well, we do, it's a hidden 1. So there's nothing displayed there, and we actually wanted to get the whole equation into this form. So all the y terms are on this side, all the t terms are on this side. So we can now split this derivative and say dy is equal to 12 sine 4t plus t squared plus 1 dt. That is the first step. Now what do we do with this? Well, it's actually quite simple. You just take, because these are derivatives, we have to undo the derivative. We have to take the integral. So we take the integral of dy is equal to the integral of 12 sine 4t. Now I'm going to split this term, plus the integral of t squared plus 1 dt. I could write a dt in there, it doesn't matter, because we're going to end up with a constant at the end of the day, because we don't have any specific or initial values. If you look in your log tables, and I think this is where a lot of you guys make mistakes, especially with integration, notice the sine term changes to minus cos. There is no variable in front of the constant. Here we have a variable in front of the constant, so we need to get rid of this. So guys, instead of thinking that you can do this in your head, I know it's going to be 12 sine over, or 12 over 4, which is minus 3 cos 4t. I can do that in my head. Rather do a substitution, and because we're working with integrals, let's make it a w substitution. So let's say w is equal to the inner term, the 4t. We take the derivative of w with respect to t, which is just going to be 4. Remember, derivative, take the power multiplied by the variable, subtract 1 from the power. But we need it in a dt form, so we can say dt is equal to dw over 4. So if we rewrite this, we've got the integral of dy equals the integral of 12 sine w dw over 4 plus the integral of t squared plus 1 dt. Let's cancel that because that'll be 12 over 4, so we're going to have the integral of dy is equal to 3, so it's the integral of 3 sine w dw plus the integral of t squared plus 1 dt. Again, let's simplify. We can take that 3 out because we're multiplying. The integral of dy equals 3 sine w dw plus the integral t squared plus 1 dt. So you see how simple it's actually become. So if we get rid of all these integrals, well, we've actually got a 1 in front of the dy. It's a 1. Let's actually put that in so you don't get confused. So what you have there is actually 1 times y to the 0 dy. The same thing here. You have 1 times t0 dt. Anything to the power of 0, you should know your laws of indices now. Anything to the power of 0 is 1. So 1 times 1 is 1. So what is going to happen here when we take the integral? We add 1 to the power, we divide by the new power. So this is going to become 1y to the 1 over 1, which is just y. We've got our 3 up front, we can leave that. Sine w becomes minus cos w plus, well, t squared, we add 1 to the power, divide by the numerator, so that's t cubed over 3. Well, t to the 0 becomes t to the 1 over 1. And finally, don't forget plus c, because we're not given specific variables. We don't know what, or initial parameters, we don't know what the variable is. So if we go and clean this up, I don't like the negatives in the front, so I'm going to rearrange it a bit. I'm going to say t cubed over 3, well, that's the same as saying 1/3 t cubed plus t minus 3 cos, we put the w back in, for t plus c, and then that is basically it. You are done. The important thing, we don't want any variable or any constant in front of that, and we want it on its own up front. So let's take a look at the next example. Let me just make sure it's in the camera. Okay, so what have we got? We've got 1 over x dy dx this time equals 2x squared plus 25. Now this just looks horrible. But if you see this, you know it's money for nothing. It's money for jam. Remember, we need to get rid of whatever's on the left of the dy dx, dy dt, dy, whatever it is. It must be on its own. So if I multiply through everything by x, because if I do that, 1 over x times x over 1 dy dx is 2x squared plus 25. I'm going to take that root and put it in a power format, which is just easier, and times x over 1 again. Well, our x's cancel here. 1 is just 1, so that's just going to give us dy dx, which is what we wanted. We're going to bring that x to the front. 2x times x squared plus 25 to the half. It still looks rather messy. Let's split our differentials up here. So we're going to have dy is equal to 2x x squared plus 25 to the half dx. Still looks messy, right? Here's the thing. If you ever see a power that's one order bigger than the other power, look to use a W substitution. I know you call it U subs. Call it a W substitution because you're going to get confused between using the variable U for it when you do not integrating factors, but when you do integration by parts. So always when you're doing the substitution, try it. You never know if it's going to work. Go with the term that has the highest order. In this case, it's our x squared plus 25. Don't worry about the half. So let's do that. Let's say w is equal to x squared plus 25. We'll take the derivative of w with respect to x. Well, it's the power multiplied by the variable in front. Subtract 1 from the power, so we are left with 2x. There's no variable there, so that falls away. So we need to get it in the form dx is going to be dw over 2x. Let's now feed this back into here. So we've got dy. We can say the integral of dy is equal to the integral of 2x times, in this case it's w to the half dw over 2x. Well, look at that magic. That's why I say when you see these things, money for nothing, money for jam, the 2x's are going to cancel. Look how simple integrals become now. The integral of dy is the integral of w to the half dw. Well, we know the integral of 1 dy is going to be y. The integral of w to the half, we add 1 to the power, divide by the new power. So it's w to the 3 over 2 over 3 over 2 plus c. We can make this a little bit nicer. We can say y is equal to, because the rule of division by numerators and denominators, we can flip that bottom one. So we can say we've got 2/3. Let's fill in our w. Up there we have x squared plus 25 to the 3 over 2 power plus c. So when you see these things, guys, really, first thing we did, multiply through by that term. We want to get rid of it. We just want the derivative on its own. Get rid of that format of the square root. It can confuse the hell out of you. Put it in a power series. Split the two derivatives to their respective sides. You have a power bigger than that one. Take a derivative and do a w sub. Then just integrate. Don't forget to add the c term. Okay, let's have a look at another one. Yeah, this should be fairly interesting. So, remember, like I said, all we're doing is we're getting this mathematical model into an algebraic model that we can use, that we can manipulate. Because to manipulate it in the calculus world is not, yeah, it's just not on. It's not cricket. So let's think about this. We've got dy over dx. If we remember our laws of indices, e to something minus something, well, we can say it's e to the x over e to the y. We can divide the two terms. We are given initial value y of 0 equals 1. Well, this doesn't look too difficult to do. We can say e to the y dy equals e to the x dx. That doesn't look too bad. And let's take the integral on both sides. E to the y dy is equal to the integral of e to the x dx. Well, the integral of e to the y is just e to the y. There's no variable in front of the y except 1, so that's fine. So we can say e to the y is equal to e to the x plus c. Of course, you're halfway there. Now you have to do all the algebraic hoop jumping to get this y on its own. Well, to cancel the Euler's number, e, we take the logarithm. So the logarithm of e to the y is equal to the logarithm of e to the x plus c. Put the whole thing in brackets. What happens here? The logarithm cancels the e, so we have y equals the logarithm e to the x plus c. And we are almost done. We've been given initial values, so we need to solve for c now. So y of 0 equals 1. So in other words, the y term is 1, is equal to the logarithm. Everywhere we have an x now, we substitute the e, the x, the 0 part, so e to the 0 plus c. Well, e to the 0 is 1. But we can't fit a logarithm of a logarithm of a logarithm in here, so now we need to get c on its own. So to get rid of the logarithm, raise it to e. E to the 1 is now e to the logarithm e to the 0 plus c. That e to the 0 we know is 1. What is going to happen here? That term is going to cancel. So c, we're going to have e to the 1 is equal to 1 plus c. So therefore we can say c is equal to e to the 1 minus 1. And we go back to our general solution and we feed in the value of c. So we can say this time, because we've been given initial values, y of x is now going to be equal to the logarithm e to the x plus e to the 1 minus 1, and you are done. So notice the separation part was very easy. The integration was very easy. Then there was a lot of algebraic jumping through hoops. But by this stage you should be pretty comfortable with algebra. Well, I hope so. Okay, here's an interesting one. We've got dy dx is equal to y over x 1 plus x. Well, let's split this. We take the y to this side, we end up 1 over y. dy equals 1, that y went there, so there's a 1 there, x 1 plus x dx. Again, don't be scared of this. We can take the integral on both sides. Oh, we know that integral. That's easy. That's the logarithm of y. But this is not so easy. But gentlemen, think of it. You've seen this before in partial fractions. You've got one term there, and you've got another term there. So we can say, before we carry on, 1 over x, 1 plus x, is equal to a over x plus b over 1 plus x. Now we want to get a common denominator, so we could say 1, we cross multiply, is a 1 plus x plus b times x, x 1 plus x, and this whole thing is going to be x 1 plus x. So we could just say 1 is equal to a 1 plus x plus bx. What we've done is they've got the same denominator, so we can equate the numerator. Well, how do you solve this? Partial fractions you've done. If we let b equal 0, we'll get the a term. So let b equal 0. Then we've got 1 is a, not b, you want to make the x term 0, not b, sorry about that, is a 1 plus 0. So therefore we can say a is equal to 1. If you go and substitute 1 plus 0, well, it's 1. So 1a is equal to 1, so a is 1. How will we get rid of this term? Well, to make a 0, we must make x minus 1. 1 plus minus 1 will give me 0, so the a term will be 0. So we've got 1 equals 0 plus b times minus 1. So therefore b is equal to minus 1. Minus b is 1, so b is 1. We can now go fill this back in. We can say the integral of 1 over y is now equal to the integral of a over x, well, that's 1 over x, minus the integral, I'm just going to split it again, just for simplicity, b 1 plus x, and don't forget the dx. Now it's just a case of running the integration. 1 over y is going to be logarithm of y. 1 over x is the logarithm of x, natural logarithm, minus 1 plus x. Well, that's fine, there's no variables in front of the x, so that's minus the logarithm 1 plus x plus c. Now it is just a matter of clearing this up. Let's go on to do another one. Again, we've seen this sort of thing. We can bring the e to the y to the dy side equals x, get rid of the root, x squared plus 1 dx, and don't forget it's to the half. We take the integral of both sides. Remember, we have something in here that is a power or an order higher than that thing, so look to do a u sub or w sub. So w equals x squared plus 1 dw dx is going to be 2 times, well, the power times the thing in front, which is, so it's 2 times 1 minus 1, so 2x, the 2 minus 1, so it becomes x to the 1. We need it in a form that we can use, so dx is equal to dw over 2x. Let's see if this is going to solve anything for us. E to the y dy x w to the half dw over 2x. Well, that gets rid of this nonsense, so we can go goodbye x. If we rewrite it, if we make this neater, we've got e to the y dy equals, well, we've got a half, because remember that's 1 over 2 now. Let's take that half to the front, integral w to the half dw. Well, integral of e to the y is just e to the y. Equals 1/2, well, w to the half is going to be w to the 3 over 2 over 3 over 2 plus c. So let's rearrange this. E to the y is 2/3, I can swap that around, times 1/2 times, well, w was x squared plus 1 to the 3 over 2 plus c. If we neaten this up some more, 2 times 1 is 2, 3 times 2 is 6, x squared plus 1 to the 3 over 2 plus c. We can simplify, equals 1/3 x squared plus 1 to the 3 over 2 plus c. Oh, good Lord. We need to get the y in its own form, so we need to take the logarithm. If we take it on the left, we must take it on the right, so we need to take the natural logarithm. So the logarithm of e to the y is the logarithm of, I'm going to put this whole thing in square brackets, 1/3 times x squared plus 1 to the power of 3 over 2 plus c. The logarithm and the e cancel. So we have y is equal to the natural logarithm of 1/3 x squared plus 1 to the power of 3 over 2 plus c, all done. So gentlemen, you can see this is really not much of a headache. It really is money for jam. I think I'm going to leave it there. You get the gist. The only way you're going to get this right is practice. You have to do this stuff till it becomes mechanical.